Hello, and good afternoon or good morning. Welcome to this webinar series hosted by Shimadzu, PFAS in Focus. We are so glad that you're here. My name is Landon Wiest, and I will be moderating today's event. I'm here with my colleague, Dr. Ruth Marfield-Vega, who will be sharing her presentation, Unlocking EPA Methods 537.1 and 533, Optimizing Your PFAS Analysis with you today. As you can see, this is the second episode of our 5-episode webinar series, PFAS in Focus. You can look at our website to find a link where you can watch a recording of our first episode. PFAS has been a hot topic for years, and now it's hitting a fever pitch. This webinar series aims to distill essential information on PFAS analysis by offering our expert insights to help you navigate challenges and succeed in your lab work, regardless of your current experience level. Shimadzu's team wants to ensure that you are empowered with critical analytical skills so that you can become the PFAS expert in your laboratory. Now let's get some logistics and orientation covered first. The webinar console has a variety of items to help enhance your experience and interaction with us during the webinar today. In the screen, you'll see the following items. The slides will appear in the middle area. Directly under the slides, you will see a resource list with clickable links relevant to the material being presented today. On the top is the widget for questions and answers. Please submit your questions during the presentation through this widget, and we will answer them during the Q&A session. Just below the Q&A box are survey questions that you may fill out anytime during or after the presentation. On the right are the moderator and speaker bios. You can expand the items here to learn more about the speakers. Finally, at the bottom pane are the icons to bring up all of these widgets in case they are minimized or hidden. With that being said, we have an information-packed webinar today, and we look forward to sharing with you. So let's get started. I would like to introduce or reintroduce Ruth Marfield-Vega, the Senior Marketing Manager for the environmental market here at Shimadzu Scientific Instruments, who is our main speaker today. Take it away, Ruth.
Thank you, Landon, for the introduction, and thank you for the opportunity to talk today about EPA methods 537.1 and 533 for testing PFAS in drinking water. Water quality is one of my favorite topics. In April 2024, in the United States, we lived a historic moment. That's when the Environmental Protection Agency, EPA, published the PFAS National Primary Drinking Water Regulation. I would like to poll our audience now and ask them to type in the chat the year when EPA regulated the last contaminant in drinking water before this 2024 regulation. We'll check the responses at the end of the webinar during the Q&A. The PFAS regulation includes 6 chemicals: PFOA, PFOS, PFHXS, PFNA, GenX, and PFBS. In the regulation, maximum contaminant levels and a hazard index were included. And the maximum contaminant level and the hazard index are the most relevant levels that we need to work with from now on, because those are the maximum amount of contaminants that are allowed in a public water system. As part of the PFAS National Primary Drinking Water Regulation, EPA also established 2 methods that are approved to support the regulation. They are EPA 537.1 and 533. The methods are similar because they are both suitable for the analysis of drinking water. Both of them also require the use of solid phase extraction for the sample preparation. But here is where the differences start. 537.1 requires the use of a polymeric solvent, and 533 requires the use of an anionic solvent. This is because the target compounds that are included in each method are different, and the physicochemical properties of those compounds are slightly different, with 533 having compounds that are more hydrophilic and are going to be extracted better with the anionic solvent. The last major difference is how each method approaches quantitation. 537.1, you use an internal standard calibration. For 533, a modified isotopic dilution approach is needed. And it's modified because before making the final calculations, you need to confirm that the compounds that will be used in the isotopic dilution calculation have good recovery through your method. Before talking more in detail about the two methods, I want to share with you one question that I get a lot. Can your LC-MS meet EPA's PFAS limits? Well, there is no straight answer to that question, because when someone asks PFAS limits without specifying which one, I cannot tell you if the LC-MS is going to be suitable to give you the concentrations that you need to achieve. As we review a few slides earlier, EPA has set different levels related to PFAS. And those levels cannot directly be linked to the performance of the LC-MS or the performance of the overall analytical method you need to use, 537.1, 533. There are some limits that can be linked with those, the instrument and the method. The limits that can be related to the performance of the analytical method or the instrument are the method detection limit, MDL, method reporting limit, MRL, practical quantitation limit, PQL, and instrument detection limit, IDL. I summarize the definition according to EPA in the slide for each of these parameters. The PQL is normally an arbitrary number, but in the PFAS regulation, these PQLs were established by EPA. MDL, MRL, and PQL can be highly impacted by the overall method precision and, for PFAS analysis, also by the variability of the presence of PFAS in the background in the laboratory. Two important things about this. One, MDL, MRL, and PQL are more impacted by the overall method performance because we use samples that go through the full analytical method to calculate them. And second, if you want to learn more about how to manage PFAS in the background in the laboratory, I invite you to watch the webinar number 1 of this PFAS in Focus series that Landon presented on December 5th. MDL and IDL are similar parameters because both are based on statistical calculations. But as I said, MDL is based on the results from analyzing samples that have gone through the full analytical process. So there is a lot of variability that can be built into the result based on the different steps, what happens in each of the different steps of the method. On the other hand, to calculate the IDLs, we use analytical standards. Going back to methods 537.1 and 533. The diagram on the slide summarizes the major steps in the analytical process. After the sample collection and shipment, when you get the samples in the lab, you need to add the different chemicals, surrogates for 537.1 and the isotope dilution analogs for 533. For the spiked samples, you need to add also the standards. The next step is the solid phase extraction that, as you probably know, includes many different steps. Once we elute the extracts from the cartridges, they have to be concentrated, and then in 537.1 we need to add internal standards, and in 533 the isotope performance standards. If you remember, I mentioned that 533 were use a modified of isotopic dilution, and that's because you need to quantitate the recovery of the isotope dilution analogs before you can calculate the concentration of your targets using isotopic dilution. And those calculations are built into the last step of the method, the analysis of your sample in the LC-MS. Let's go back to the question. Can your LC-MS meet EPA's PFAS limits? When we are running EPA 537.1 and 533, MDL, MRL, PQL are going to be impacted by all the steps that are summarized in the diagram in the screen. So when someone asks me about the LC-MS limit that can be achieved, I like to talk about the instrument detection limit, and we'll get back to that point at the end of the webinar. In the next slide, I'm going to share the work that Shimadzu has been doing on PFAS testing for decades in collaboration with customers and other partners like Millipore Sigma. The outcome of this work are optimized methods. Today, I'll be talking about EPA 537.1 and 533, but we are going to be talking about other methods in upcoming webinars. And these solutions we created will enable you to start running your initial demonstration of capabilities as soon as you have the instrument installed in the lab. We've pre-optimized everything for you just to start running your samples. The table in the screen lists the target compounds in both EPA 537.1 and 533. As you can see, 533 has more targets than 537.1. The chromatogram is an example of the results that we get for 537.1. The cycle time for this method is 18 minutes, and for 533 is a little bit shorter, 15 minutes. In both cases, this cycle time is more than 50% shorter than the original methods from EPA. The reason for having those 3 minutes difference between the two methods is that we observed some carryover from some of the PFAS compounds in 537.1. So we built that extra rinsing time to make sure that there is no carryover. The work I'm presenting today was done with an LC-MS 8050. That's a mid-range instrument in terms of sensitivity. We have other models that are a little bit lower sensitivity and much higher sensitivity. The calibration range was between 0.5 and 15 nanograms per mil, and that's concentration after the solid phase extraction step. The specific concentrations of the compounds changes because we use pre-mix standards that are created with different concentrations for the targets. And in this work, we use just 2 microliters for the injection. That's 5 times lower than the original method, than the original volume used in the EPA methods. When I was talking about the cycle time and the chromatography, I forgot to mention something very important. With the optimized chromatographic methods that we've created, we meet the peak symmetry criteria in method 537.1, and we also meet the criteria for isomers separation. Now, another parameter that is essential and it's required in 537.1 and 533, and that's the demonstration of low system background. The method says that the laboratory reagent blank, or LRB, has to be less than a third of the method reporting limit. During the testing that I'm presenting today, as well as years of running experiments, we can check the low background not only following EPA's criteria, but also by running by running null injections. The null injection is an injection of only mobile phase. There is no external sample introduced in the system. So basically, it's a plug of solvent that goes through the gradient and runs through the whole system. With a null injection, we can confirm every day that our mobile phases are clean, our delay column is working and is delaying potential PFAS in the background, and the rest of the hardware is also clean. In the specific experiment shown in the screen, our blank was 4% of the MRL, and that work was done using consumables from Millipore Sigma. Now some performance results from 537.1. We calculated IDLs and MDLs following standard guidelines, and after confirming that all compounds met the requirements of precision and accuracy, as well as the upper and lower PIR values, and as I mentioned earlier, the isomer separation and asymmetry. The IDLs were between 0.2 and 1.2 nanograms per liter, and the MDLs were between 0.4 and 0.8 nanograms per liter. For EPA 533, similar results. All compounds met the precision and accuracy requirements described in the EPA method and the upper and lower PIR values. Also, instrument detection limit was between 0.2 nanograms per liter to 1.4 and the MDL 0.4 to 1.3. Now let's take a quick look at the software. And here I have a couple of screenshots of the LabSolutions software. The bigger picture gives you a quick overview of what's the landing page when you come every day to start your work with the instrument. And the smaller picture in the bottom corner gives you an example of a batch table that we have created already according to the requirements listed in the method to run the samples according to 537.1 or 533. And now the fun part, processing the data. This is a screenshot of LabSolutions Insight, and then in the next couple of minutes, I'm going to play a video for you so you get to know more about LabSolutions Insight.
Hello, my name is Megan Davis and I am a LCMS product specialist here at Shimadzu. This is a quick video on how to review and process quantitative data in Insight. LabSolutions Insight is a software designed to swiftly process and review large quantitative data sets. Select LabSolutions Insight LCMS and enter the appropriate user information. The default is admin as the user ID and no password. LabSolutions Insight can easily be customized for different views that will suit each user's needs and automatically saved for each user. Commonly used functions in Insight can be added to the shortcuts list for ease of use. Data can be brought in by batch, method, a single data file, or saved project file. Depending on the preference of the user, the view can be changed between sample view and compound view. Both survey and QC chart allow a quick overview of the dataset. The Edit Tables function allows the user to edit sample and compound information. Sample type can be adjusted to standard, unknown, control, and several others. Calibration level, compound type, and internal standard group can be adjusted to set standards in accordance with the compound table. Once completed, click on Edit Tables again for the changes to be effective. Other parameters with a pencil can also be adjusted in this way. The standards to be included in the calibration curve can be adjusted by unchecking and checking cal points. Users can adjust the curve fit, weighting, and zero fit from the calibration window. Under Compound Detail, the peak integration can be adjusted and reviewed. To manually integrate a peak, simply right-click on the peak and select the integration type. The quantitative ion can be selected under this review as well. Retention times and ion ratios can also be updated by right-clicking. For more advanced settings, Edit Method will allow the user to address the data processing method, which includes integration parameters and calibration level concentrations in the compound table. For more information about Shimadzu mass spectrometers and software, visit us at www.ssi.shimadzu.com.
You learn about the flags that can be built in LabSolutions Insight. And now let's learn a little bit more about how we can do that. Very important when you are validating your methods and you are running samples in support of the PFAS regulation.
Hello, my name is Megan Davis and I am an LCMS product specialist here at Shimadzu. This is a quick video on how to use flags. Using the flags in LabSolutions Insight provides the user with efficient tools for data review by exception, maximizing the time of the analyst. Select LabSolutions Insight, enter admin as the user ID and no password, and hit enter. Open your data in LabSolutions Insight. Select Edit Flags in the Edit menu of Insight to make new flags. Select the +- tab to add the flags for specific sample types. Then select Edit to add the types of flags that will be evaluated for the sample type. Flagging values can be typed in, or the box can be right-clicked to use defaults or fill the value down. Some flag parameters, such as accuracy, can have the value set by the concentration level. Select the result to modify how the flags are reported. Flag parameters can be set to fail or be inconclusive if all the sample type or any type of sample is found outside of accepted values respectively. Custom text can also be set based on the flag result. Samples and compounds that are flagged will be highlighted with the color corresponding with the flag parameter and value. Flag results are also colored differently for ease of use. If flags have already been set up for compounds, they can be loaded into the project using the Load Flags button under File. The unknown sample type has a lower and upper concentration limit in review flag parameters. Unknown samples with concentrations outside the set values will have different colors. The colors used for flag colors and results can be set in application configuration in the common display settings under flag colors. For more information about Shimadzu mass spectrometers and software, visit us at www.ssi.shimadzu.com.
Now, let's go back to the beginning of the webinar, when I was talking about the practical quantitation limit, PQL, the instrument detection limit, IDL. If you remember, I said that the PQL in the PFAS regulation is set by EPA, and those are the numbers that are included in the table in the first column. In the second column, I summarize the instrument detection limits that we obtain with these methods that we are developed and we are ready to share with all our customers. And then in the last column, I have the ratio between the PQL and the IDL. Since the PQL is much higher than the IDLs that we obtain, that's why those numbers are larger than 1. What means that our instruments are sensitive enough to help you achieve the PQL required under the new PFAS regulation. I gave you a brief overview of the results that we obtain from these methods in relationship to the requirements in the initial demonstration of capabilities. And if you want more details, you can download the application notes that are included in the resources of this webinar. Before closing the webinar, I want to take a few minutes reviewing some analytical chemistry concepts that help with improving the method performance for PFAS testing. I pick 2 concentrations, 10 and 4, since those are the maximum contaminant levels included in the PFAS regulation. Those concentrations are in ppt, nanograms per liter. When we do the solid phase extraction, basically we take an aliquot and we pass it through the cartridge. So we trap the full mass of the compounds present in that aliquot into the cartridge. So if we had 10 nanograms per liter or 4 nanograms per liter in our sample, and we extract 250 microliters. Ideally, if we have 100% recovery, we'll have 2.5 or 1 nanogram, depending on your initial concentration. Then we concentrate the extract down to a final volume of 1 ml. So the concentration in that extract will be 2.5 nanograms per ml if we started with 10 ppt, or 1 nanogram per ml if we started with the 4 ppt. And finally, if we inject 2 microliters from that extra, we are actually injecting only, we are only sending to the detector 0.005 or 0.002 nanograms from all that amount that started at the beginning. So we are truly wasting a lot of mass. Why did I go through all those calculations? Because I wanted to remind everyone some of the basics that we learned in the analytical chemistry classes. And especially because if we want to improve the sensitivity of our method, what we are truly doing is increasing the mass of the compounds of interest that makes it into the detector. EPA methods 537.1 and 533 have some parameters that cannot be modified. For example, the sample volume to be extracted in 537.1, it cannot be changed. But in 533, you can do it. It has to be between 100 and 200 mL. The final volume of the extract after the concentration with nitrogen cannot be modified. It's always 1 ml. So if you have the same sample volume, but you use a larger sample volume, you are going to have more mass going to the detector, and that translates in lower detection limits. A parameter that can be modified is the injection volume. The methods that EPA publish use 10 microliters. The work I showed today, we use 2 microliters for the injection. And we achieved instrument detection limits that were sufficient to meet the PQLs. But if we wanted to improve the sensitivity and lower the detection limits, we could still increase the injection volume a few more microliters. In general, for PFAS, if you want to improve the overall performance of the method, don't forget to use the delay column. I refer you to learn more about that to our first webinar of this series, and know your consumables and reagents. And what I mean by that is that you need to test them to check PFAS in the background, but you also need to understand the impact, the quality of the reagents can have in the signal in the LC-MS. And of course, minimize the bias in your workflow. I'm going to poll our listeners again. I like to ask people how you feel about PFAS right now. Are you prepared, frustrated, anxious, successful? I want to see the responses in the chat, and maybe later I tell you how I feel about it. Well, jokes aside, thank you everyone for listening today. If you have any questions or need additional information, we are going to take care of questions in a few minutes, but also don't hesitate to contact me. Thank you so much. Oh, and one last thing before passing the mic to London. In April of this year, right after the EPA published the regulation, I had the honor to participate in a webinar with my friends and colleagues, Andy Eaton, formerly with Eurofins, Eaton, and an international key opinion leader in environmental testing, and Alicia Boca, that is the lab director of Aqua, one of the first utilities to start responding to PFAS while we were going through UCMR 3. If you missed the webinar and you want to watch it, you can access that in our website. And you can learn there a lot of things from what we learned about PFAS, our successes, and I hope you enjoyed. Thank you again.
Thank you, Ruth, for your wonderful presentation. And thank you for contributing your knowledge so that we can make all our listeners the PFAS experts in their labs. If you would like to see the topics that we will be covering in the upcoming events, scan the QR code on your screen. This will give you access to the specific dates and allow you to register for all of our future webinars. During the next presentation on January 9th, we will present Accelerating PFAS Detection in Complex Matrices by EPA 1633. And now, I would like to open it up for Q&A with questions from our chat. As a reminder, if we do not get to your questions live, we will follow up via email.